Hello everyone. In this video, we are going to look at a few advanced metrics for goodness of fit. If you watched my previous videos where I talked about curve fitting, you know that when we want to assess which model is good for the function that we assume, the underlying function, one of the most common metrics that I mentioned is R squared, and you can see it in MATLAB, in Excel, in so many places. And you know that R squared is 1 minus residual sum squared error to the total sum squared error, where residual is the difference between actual data and the estimated data from the function, and the total is the subtraction of the data from their average. And it shows basically how much of the variation in the data comes from your model and how good your model is compared to just saying the data can be represented by their average. Okay. So you know this number is typically between 0 to 1. The closer to 1 it is, that means this residual term is almost 0, which means your curve almost passing through all of the points. And that is like a perfect fit, which most of the time doesn't happen due to measurement noise and so on. The closer it is to 0, that means your function is only as good as just saying the data are the same as their average, which basically means no underlying function, just a constant number. So what is the problem with this? Why do we need to come up with other metrics? And the reason it came up for this video is in the class when I was showing my students the MATLAB curve fitting app. So here I imported some data from a cubic polynomial with some noise, and I wanted to show them that you can pick your function here, and let's say if you pick polynomial, you can change the order here and so on. Then here is the best estimate for the parameters you have, and then down here you see goodness of fit. And of course sum squared error and root mean squared error are quite a bit obvious, but I talked about R squared for them. And then there were these two guys, the degree of freedom error and the adjusted R squared. So they asked me, what are these? And I said, you know what, let me make a video so I can explain it to them as well as everybody else. So I want to explain DFE, adjusted R squared, and a couple of other metrics, AIC and BIC. Okay, so let me tell you what these metrics are and why should we have them in the first place. Well, the first problem is if you look at R squared, which is the most common metric that we know, one problem with it is it does not go down if you add more predictors. And what is predictor? So if you have a multi-regression like y equals, for instance, beta naught plus beta 1x1 plus beta 2x2. So here your predictors are x1 and x2, or your independent variables, right? So you have two, and you can have one for this bias or constant term. If you have a polynomial, so you have beta naught plus beta 1x plus beta 2x squared and so on. Again, it's similar. So here, each one of the polynomial terms now counts as a predictor. So you still have like 3 terms or 2 terms if you don't count the constant. So the problem is if we add more of these terms here or here, the R squared does not go down. In other words, we can easily go toward overfitting by adding more and more terms, adding bigger and bigger, more complex polynomials, more complex models, and this R does not go down. So to R squared. So to R squared, a polynomial of order 3 could be as good as a polynomial of order 10. And we know that we should not overfit because higher order polynomials or functions, they have typically oscillations and they can overfit. So we want to have something that penalizes higher order terms or more predictors and avoid overfitting. So how do we do that? Well, one of the metrics that is not really that useful, but since it's in that app, I want to explain it. That is called the degree of freedom error, or DFE. It's just how many independent pieces of information are left to estimate the variance, and this is n minus k plus 1, where k is the number of your predictors. Why did we add a 1? That 1 is for the constant term, and n is the number of data. Okay, so what does that mean? If I go back to this picture and show you, so here I have 50 data points, and I only have a polynomial of order 3, which means I have 4 constants. So k is 3, k plus 1 is 4. So I have only 4 constants to find, but I have 50 data points to pass through. So I know there is no way I can pass through 50 points because I only have 4 parameters to tune or control. So the difference between that 50 and that 3 plus 1, which in this case is 46, this is the number of points that I cannot really pass through, and this is the amount of variation in the data that is not coming from the model because of the randomness. And you can see that in this case now, actually, my bad, so it was 100 data points, not 50. Let me look at my code here. Yeah, it's 100 data points, not 50. So sorry for that. So in this case, I have 100 data points, not 50. Therefore, my DFE is going to be 96. Okay, and you can see that it is shown in this app over here. So now going back, how does this help? Well, since my data is fixed, or if I assume it's fixed, the bigger order of polynomial that I use, the bigger the k I use, this DFE is going to go down. Okay, so with more complex polynomials or bigger predictors that I pick, this guy keeps going down. So, but it has a disadvantage. What is the disadvantage? The disadvantage, it keeps going down all the time. So if you look at this plot here that my code generates, the DFE keeps going down. When I start from a line, it's 98, and then it goes to 97 and 96 and 90, and then ultimately 4, and go down all the way, and at 6 it is 93. Okay, so if I want to see which one of these polynomials is the best one, if I want to do an optimization or pick up my best degree, it says probably what? If you look for the maximum one, it says your line is the best one. What? Well, in this case, it's not really the line. My underlying data are coming from a cubic polynomial. Okay, so the bad thing about this is it doesn't have a minimum or a maximum point. It is an basically constantly decreasing or monotonically decreasing function, monotonous decreasing function. So it cannot really be used to pick the best number of predictors. But if you look at adjusted R squared, which is a little bit more sophisticated, this is quite a bit interesting. So what is this one? This one is 1 minus r squared, but times n minus 1 divided by n minus k minus 1. And now the thing is this. First of all, you can show that for the same n and for the same k, this guy is always a little bit smaller than the actual r squared. So this is a little bit smaller than r squared. And this one will only go up, and you know, bigger r squared closer to 1 means better. It only goes up if, when we add to this k, that will improve your model. So this one actually does have a maximum in it. Okay, for some k, this guy will reach a maximum, and after that it starts going down, because after that k is increasing, but your model passing through the data, some residual squared error is not necessarily going so much down. And it can even go negative if your model is now super complex. You have too many k's, too many parameters, and you're not doing any good. So here is the result of the adjusted R squared and DFE. I have applied different polynomials starting from order 1 to order 6 to these underlying function that is cubic. And you can see that as I go from the first order to third order, look, my adjusted R squared gets bigger. And then once I go to 4, 5, and 6, you see it's slightly decreasing. And as I go further down, if I go, this guy keeps going down. DFE, no, you see it just keeps going down. So clearly, if I look at the value of adjusted R squared for different polynomial orders, you see that I have a peak here, and that is at 3. And there is a very small slope here, but clearly the peak happens at 3. And you can see that here. And so this is the good thing about the R squared. It tells you the same thing as R squared does, which is basically how much variation can be explained by the model, but it adds an adjustment for the model complexity to it. There are 2 other metrics that are not implemented in MATLAB, but I just want to mention them. One of them is called AIC, if I'm pronouncing it correctly. It's called AIC. Yeah, it's a Japanese name, AIC. I assume the person who came up with this metric. And you can see that the number of data is here. The natural log of sum square residual divided by n is there. And 2 times k plus 1, where k was the number of predictors, or k plus 1 was that including the constant. Now, this one, basically, when the model has a good balance of fit and complexity, it has minimum value. So as opposed to adjusted R squared that has a maximum at the best model, this one has a minimum at the best model. Okay, and as you get away from that, the function increases. And you can see that here in this plot, that you see as you go from 1 to 2 to 3, it goes down. And as you pass from 3 to 4, 5, 6, it goes up. So clearly, clearly this AIC and the next one BIC, which are very similar, these guys both have a minimum, and their minimum is indicating the best polynomial order in this case, or the best complexity of the model. So you see it is going down, the biggest negative number, and then keeps going up again. Okay, so this is called what? AIC. And there is another one which is called Bayesian Information Criterion, or BIC, and it is actually derived from a Bayesian model evidence, okay, or marginal likelihood we call it. So I don't want to go into the derivation or anything of that here, but it is actually kind of related to the Bayesian model. That's why there is the Bayesian in its name. And if you look at it, it's very similar to AIC. So the first term is exactly equal. The only difference is here, the term multiplied by the total predictors is 2. Here is natural log of n. So the penalty term here is just 2 times k plus 1 is constant. This one depends on n. So when n is kind of small, so natural log of it is about 2. So it's like e squared, something like 5, 6 data points something. They generate similar numbers. But as your number of data gets bigger and bigger, 100 points, 1,000 points something, the penalty term here is going to be much bigger than the penalty term here. So I can say this one penalizes the complexity more strongly compared to what? To the AIC. And this one also has a balance, and the minimum value of that typically indicates the best degree of freedom or the best complexity. The good thing about it is, as I said, it is sensitive to n, so it is really good when your model is has a lot, where your data points are very large. If you have lots of data points, this could be very good. And again, you can see that here in the data, and you can see it here in the plot. Okay, and you can see that the numbers of AIC and BIC are quite a bit similar, but not exactly similar, because in this case n is 100, not like a small number. Now, if I want to compare adjusted R-squared, AIC, and BIC, since these three can show you an optimum point, I can say that R-squared is really good because the interpretation of that is relatively intuitive. The thing is, it can still favor very complex models if n is small. And you can see that here, that when the n is increasing, although the function goes down from 3 to 4, 5, 6, but it's not like a big decrease. Okay, so the peak point here, I mean, up to this point, you can clearly see the increase, but after that, it barely decreasing. Okay, and n still not huge for this. Okay, so 100 points still not a lot, but maybe if I make it 1,000 points, it can show some better peak compared to this. AIC, as you could see, it does show a better minimum. Okay, and they are negative numbers, and their absolute values are not necessarily meaningless. It's the relative position that matters, and the very smallest, the number that is the most negative, basically, is the one that is the best. And of course, if n is small, still this guy may overfit, might favors toward moving toward a bigger case. So if you basically have small n's, AIC can overfit. On the other hand, BIC can underfit. So if you have large n's, BIC is always the way to go. If you have small n's, you probably want to get to something like AIC, although it might overfit, or a combination of them. So I would say, if you again want to have some interpretable measure, adjusted R-squared is good. But if you want to see the peak point, the best model, AIC and BIC are a lot more sensitive to it, especially when n is large. BIC is the better method to go. When n is small, each one of them can have some problems. One of them can overfit, one of them can underfit. But that is another thing that you have, is when n is small, you have to make sure your k is quite a bit small too. Okay, so as much as possible, or you want to make sure you get more data, so your model is more meaningful. Because if your function is only fitted to a few data points, generalization of that and using that is not really good. That's another thing that I talked in one of my previous videos. It was called the sample size and the test power. So when you want to do something, when you want to get data, when you want to fit a model to it, you always need a reasonable number of samples so your function can be reliable, the one that you fit, or any conclusion that you get out of the data still is meaningful. So I'm going to share this file with you, this one here. Feel free to change it to any way that you want and play with it. And hopefully you learned something useful about the metrics for goodness of fit. Thank you. I'll see you in the next video.